Thank you all for coming to this presentation. I'm going to talk about a really cool project that we did at Orbital looking at using artificial intelligence to distribute aid across the developing world. I don't want to give you this huge synopsis of what Orbital does, but essentially we're analyzing satellite imagery using convolutional neural nets and determining economic trends from these. We do a lot of work across all kinds of different businesses, but this is one of my favorite projects to show off here today, so thanks for being here. So here's the problem. This is a picture of Mexico, and what you see is this luxury high-rise tower next to a shanty town. So Mexico is developing very, very quickly. They're building a robust world economy, and this could apply to many other regions of the developing world. But the gains of this new economy are being distributed really unequally to different classes of people. So there's organizations like the World Bank, and that's the organization we did this project with, that's trying to distribute aid to the people who need it most. So they have a problem, though, is the way the World Bank understands how to distribute aid is based on a census map at the state level that's only updated every 5 years. So what this is this is the most recent World Bank map. It's from about 5 years ago. And you can see that there's a little green blip of very little poverty in the south at Mexico City. You can see that Quintana Roo is not doing as well, that Baja is somewhere in the middle. And this is all the World Bank economists have to determine where to distribute their aid. So they said there has to be a better way because Mexico has changed a lot in the last 5 years. And maybe Cabo at the southern tip of Baja is actually quite wealthy. And we need to look at Cabo a little bit different than, say, San Quintin to the north, which is quite poor. So people have been working on solving this problem for a long time. On the left is a map of, this is actually Sri Lanka, not Mexico, of building heights. So this was an old project that Orbital did. And we were looking at the shadows cast by buildings to serve as a proxy for economic development. So the theory is that as economies are building taller and taller buildings, the economy is improving, there's more money going into that area, and there's less aid necessary in that area. This is really noisy, it's really messy, and it's a very imperfect measure of economic well-being. The second is from what's called a VIIRS satellite, so it's a nighttime light satellite. You've probably heard about this. This is a very popular way to measure economic development, and the theory goes that if somewhere has electricity at night, or is burning things at night, or is somehow contributing to this signal of nighttime lights, then it's probably developing. So we can look and we can see how a country is developing by how bright its light is at night. There's a couple problems with this, though, is the pixels are actually quite large, so you can see that every city would be developed. So all this would tell the World Bank is it a city or is it not a city? And the World Bank already knows that. And the other point is it's a very insensitive measurement. So there's people trying to do this with China right now where they're looking at how bright these Chinese cities are, but it's more of like a threshold. It's more of like a neuron firing rather than any kind of sliding scale of income inequality or wealth. So we thought that there was a better way to do that, and we started looking at imagery from space. So these are just two example images. To the left is Mexico City, which is one of the wealthiest areas of Mexico. And to the right is Santiago, which is a city that's one of the poorest cities in Mexico. And us as humans can see very quickly that there's something different about these two images. Mexico City has paved roads, it has lots of trees, it has this nice geometric outline of neighborhoods, it has consistent red roofs, and it has a lot of features that you might believe to be associated with areas of high wealth. Then you turn your eyes to Santiago, and you see it's dirt roads. You see the trees are kind of clustered between neighborhoods. They're not planted trees. It's just kind of built around a forested region. You can see that the buildings are smaller, that everything is less regular, and that this particular region has some features that are quite different. So you might say, all right, that's great. I want to look at all of the imagery in Mexico to determine which areas are poor and which areas are rich. So you say, okay, how might you do that? And it turns out this used to be really, really, really hard. So in the old school version of computer vision, each rule was hand-coded. So what I have on the right here is a hand-coded classifier for clouds. This is just one feature. This isn't red roofs versus brown roofs versus big roads versus small roofs. This is one feature that's blindingly obvious. It's white, it's fluffy, and it's found in a lot of satellite imagery. So you can look at the logic. We're going to say, is this a potential cloud layer? We're going to split this cloud layer into a couple of classes. We're going to look for edges using maybe some convolution. We're going to look for colors. We're going to look at the shadows that are cast next to the cloud. This is very, very hard to do. This is very hard to hand code these rules. And this has been the state of the art for computer vision for a really, really long time. But what's amazing is something called deep learning has come along. So I'm sure everyone's heard a lot about deep learning recently, and this is just taking the computer vision world by storm. So how this works is instead of hand coding each individual rule and saying, red roof, if red roof, then probably rich, if brown roof, probably poor, and having that very, very rigid rule set that will determine how wealthy an area is, it's a black box that is filtered through a bunch of neuronal activations into a final answer. So how this works is you have a set called training data. So I've kind of simulated the training data in this picture with the blue and green mask here. So that blue and green mask actually represents like the last census poverty data that came from the World Bank. So each one of those individual households is colored based on the income of that individual household. And then that's compared with the satellite data from that area, which is the image to the bottom right. And then what happens is every single one of those pixels is run through this convolutional neural network, which is the underlying technology below deep learning. And each signal is passed from one neuron to the next neuron to the next neuron until it gets to the final one. And the final one has basically two answers. It could be poor or it could be rich. In this case, it's a little bit more complicated. It's not just a classifier. It's trying to predict the income. But that's a simpler way to think about it. So it's either this picture in the upper left or this or in the upper right or this picture in the lower right. So how this works is each pixel is then given some activation function, and that's going to propagate through this entire network, and it's going to be compared to that actual ground truth, which is the picture in the bottom. And then if we get it right, the pixel values are all adjusted accordingly and jiggled through this entire network to determine the correct value. And then eventually, you have a very strong signal that can propagate from data you've never seen before into data to solving the problem that you want to solve. And this is a really amazing technique that's revolutionizing all kinds of computing right now. Everything from determining text from speech to doing aid projects like this. And this just works. So this is just a black box that you train it, you give it enough training data, and it will determine very quickly and pick up on features that will sometimes the human eye wouldn't even know about. So this is an example of the result. So before I showed you something that we knew about, so that was called part of the training data set. This is the result. So from the results of the neural net, I picked out one of the richest and one of the poorest areas that we determined by this computer vision technique. And on the left is Monterrey. This is one of the richest towns in Mexico. I think this is the second richest town after Mexico City. And it has a per capita GDP of $30,000. Then Felipe Carrillo Puerto is actually has half the wealth. And you'll notice that just like our eye picked up the differences between those two photos, so did the neural net. And this is really incredible. And you can actually run this backwards to see what types of features it's picking up. And again, it's the width of the streets, it's the organization, it's how close buildings are to each other. And this is a really amazing technique that has been able to change how we're looking all across the world. And what's also amazing about this technique is it scales. So we can run this same software distributed in processes all across the cloud. So what was once a knock on doors every 5 years to try to get at the poverty level in Mexico, now we have, I think for this project, it took 200 different machines a few days to actually run this each quarter when we run this. So each satellite image goes to, or each group of satellite images goes to a different machine, and then that machine is responsible for determining whether an individual area is poor or rich. And then because it can be scaled across so many machines, it actually, not only it scales across Mexico, but it scales across the entire world. So all of a sudden, we have a worldwide system for determining poverty from space, which is something that has never been done before. So you might say, okay, this is great. You can show me some good examples, but how does this actually work? So this is our final map of Mexico that has never been shown off before. And this is at the county level, but this can actually be done at the neighborhood level. We can tell the World Bank, this neighborhood is in need of aid, and this neighborhood is doing really well. And then we can look and we can run it again a year later, and we can say, this neighborhood is improving because of that aid, and this neighborhood is not improving because of that aid. So this is this more granular level of Mexico, and this estimate is the urban poverty estimate. There's a different map we did for rural poverty for various reasons. The World Bank wanted these two split up. And this is the first time that they've had this, this level of granularity going into their estimates of poverty. And what's even more incredible about this is some of the features that we're picking up to determine poverty can also be used for other things. So as part of this process, we're automatically getting how many buildings are there, how many roads are there, how much water is there. So now, when the World Bank says, okay, state of Quintana Roo, we believe that if we build more roads in this area, you're going to lift yourselves out of poverty. We can go and we can look at that area, and we can look at that area after they distributed the aid, and we can say, A, how many roads did this money actually build? Because this is an unknown question in some developing areas. Did the money actually go where it was supposed to go? And then B, how many buildings, which again are this measure of lifting out of poverty, went along these roads? And then overall, look at this poverty index and see how that particular municipality did with the aid. So again, this is the first time that we've been able to build a poverty mapping system that scales across the entire planet. It's taking satellite imagery from all different providers and merging it into this big convolutional neural network. From there, we're able to determine a poverty score and then let the World Bank determine where to allocate their aid based on that poverty score. So thank you, and I'll pass it on to the next speaker.